Hello, algebra students. Today we're going to do more factoring, factoring quadratics, and we're going to be looking at perfect squares. Um, that is, A and C are both perfect squares in these examples we're going to do. Okay, so let's get started. The first one we see has only two terms. And look at B, it's similar, right? Only two terms. There is no middle term, no x term, so to speak, with bx. So we would say B is 0 in these first two examples. B in the general form is the coefficient of x. Well, it's 0 because we don't have an x term. So when you have these, you look for, are both terms perfect squares? If so, it's a difference of squares and it can be factored very easily. So this first term is 4x squared. Well, 4 is 2 squared, right? And x of x squared, of course, is x squared. So we can write that term as 2x quantity squared. 2x in parentheses, and that whole thing is squared. And again, when you write that down, check it. Okay, if I do square that, the 2 will distribute, and that will be 2 squared times x squared, and that is 4x squared. So we can call that distributing with the exponents. That's one of the rules of exponents. So that does work. 2x quantity squared is, in fact, 4x squared. So we will now write 16 in that form as something squared. So yeah, what's the square root of 16? It's 4. Okay, so now we have this written as a difference of squares. And when you have a difference of squares, it can be factored very easily. It's that first thing that's squared, goes here and also here. And then the second thing, whoops, which is the 4, it goes here and here. And notice the first one was minus 4, and then you have plus 4. And of course, you could do it the other way around. It could be 2x plus 4 times 2x minus 4. Either way, usually we put the 2x minus 4 first. It seems to be the conventional way, but it doesn't matter. So that is now factored. It's just that easy if it's a difference of squares. So let's look at the next one. No middle term. Is this a difference of squares? And to make sure we can write it as 5x quantity squared minus 7 quantity squared. And there, that's it, right? That's a difference of squares. You square this 5x, you'll get 25x squared. So, simple enough. We simply break the parentheses. And that's it. 5x is the first term in each binomial, and then the first binomial, you take 5x minus 7, and the second one, 5x plus 7. Okay, the 7, of course, comes from here. It's the other thing that's squared in the original quadratic. Okay, so the next two examples have 3 terms. And they do have a middle term. The first term is a perfect square, and the last term, the C, is a perfect square. And for this to work, B has to be something very specific. So let's look at that. What does B need to be? If we write these the A term and the C term as squares, 4x squared, of course, is 2x quantity squared, and 25 is 5 squared. So the term in the middle has to be, in this case, 2 times 2x times 5. Okay, so the 2x is right there, the 5 is right there, and it's the product of those, but then times 2. Okay, and 20x is indeed that. It is 2x times 5. Again, the 2x comes from there, the 5 comes from there, and then times 2. So 2x times 5 is 10x, times 2 is 20x. So this one does fit the form, and since it does, we factor it very easily. It's this 2x and then we could put the 2x both places, and then it's plus 5 and plus 5 again. Okay, it's not the plus or minus thing, it's just plus 5 both in both binomials, and we could write that as 2x plus 5 quantity squared. Okay, so the next one is similar, but just a little bit different. We look at it, and again, the a term, the x squared term that is, and the constant term, which does not have a x at all, they are both perfect squares. So then we have to ask ourselves, does the middle fit the pattern? And we also have this pattern if it's subtracted, okay, as long as it is 2 times the square root of this first term times the square root of the last term. We'll see what that looks like. So when we write the first term as a square, that's 3x squared. We write 4 as a square, that's 2 squared. And then in the middle, this pattern works for minus as well, but what we want to see here is 2 times the 3x times 2. Okay, and this 2, of course, is different than this 2. The one with the arrow, that's always part of the pattern. Okay, and this 2 that I'm underlining here, the last one in that product, that just comes from here. Okay, the C term. So does that work in the middle? Well, yeah, negative 2 times 3x is negative 6x times 2 is negative 12x. Okay, so if it does fit the pattern, but since this is a minus sign this time, it goes like this. Whoops. Oh, let's see, yeah. 3x minus 2 times 3x minus 2. It's just the sign of the middle term. Okay, it's negative this time. It was plus for that one, and since it was plus, then this is plus inside, which we can show down there. And of course we can write that as this one as 3x minus 2 squared, and that minus inside the binomial is because it's minus here, okay, in the original quadratic. So that's the perfect squares, the two patterns that we have. One, when it's a difference of squares with no middle term, and then you get something like this, where you have the first binomial subtracts that number and the second one adds it. And then you also have the pattern where you do have a middle term, but the middle term has to be exactly right. Okay, it has to fit the pattern that we looked at, where it's 2 times the number that's squared in your first term, then also times the number that's squared in the last term. So in this example C, 2 times 2x times 5. As long as it's that, the pattern works, and you factor it like this and you get the easy, quick answer. So to do these problems, you just have to look and make sure one of these patterns is holding in that example, and if it is, you go ahead and factor it in this manner. I think what we didn't do is check any of these, and let's do a couple of them. Look at A. Let's go ahead and multiply this back just to see, make sure it works. So we have 2x times 2x, that's 4x squared. You have 2x times positive 4, that's 8x. And then you have negative 4 times 2x, negative 8x. And negative 4 times positive 4 is negative 16. And of course the middle term cancels out, and so it does check. There it is. So you see why this works the way it works, because this first one is minus and the second one is plus, it ends up canceling your middle term. And that's why in these you have no middle term. On the other hand, on the ones that do have a middle term, in your binomials, they're both plus, right? You have plus here and plus here. They're both plus, so they're not going to cancel that middle term. Instead, you'll have the middle term twice. Let's go ahead and see what that looks like. I say you'll have the middle term twice. It'll add together to create that final middle term that you actually get. So it looks like this. Okay, let's FOIL that out. 2x times 2x is 4x. 2x times 5 is 10x. And then 5 times 2x, well, that's 10x. And 5 times 5 is 25. So sure enough, you get 20x. It's that middle term. Okay, and it comes about as 10x plus 10x. So yeah, the pattern is it'll be 2 times that 2x times 5 deal, because that's what we have right here, right? We have 2 of those, 2x times 5, which is 10x. So that's it. You're just, to do the homework, you're just looking for that pattern, and one of these two patterns, either difference of squares or this sum where you have the first term is squared, something squared, the second term is something squared, and then the middle term is just right to be 2 times the product of that thing that's squared for the x squared term and thing that's squared for the c term. Now, and the other one is where it's minus 2 times that. Okay, like this. Okay, so you might think of that as 3 patterns or 2 patterns, but it has to fit one of those. And if it does, then you do it like the examples.